Hello, everyone. Good to see you again. I hope all you are doing very well. In this video, I'm going to introduce another basic model of aggregate demand, market share model. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. In this lecture, I'm going to introduce another important basic model for analysis with macro marketing data. In some markets and industries, no two brands are exactly alike. One brand is differentiated from the other, and consumers usually choose one of the brands in the market per each choice occasion. I first introduced this kind of market, a differentiated goods market. Then explain how to describe consumers' discrete choice behavior in such markets. However, in market level data, individual consumers' choice is not observed. Instead, market shares of the brand are generally used for analysis. I'm going to introduce the share inversion method, which is a useful technique to derive market share analogies from discrete choices. Then, I'm going to derive price elasticities under a market share model. Okay, are you ready? Then, let's get started. Let's think about markets of soft drinks, pharmaceuticals, potato chips, cars, and air travel. In those markets, there are a large number of products competing against each other. And each brand product is different from the others. That is, products in such markets are differentiated. And consumers typically choose only one of the brands, which is called discrete choice. In such differentiated goods market, the market share of the brand is the key metric of demand and sales, because the demand quantities are generally proportional to the market shares. In order to explain a brand market share, let me start with a model for consumer discrete choice. Consumer choice is generally described by picking up a brand that gives the best bang for the buck, which is utility for $1. For example, consider a chocolate chip cookie market. For simplicity, suppose that there are only two players in the market, Chips Ahoy and Keebler. And suppose that there is a consumer who feels 10 units of utility from Chips Ahoy and feels 8 units of utility from Keebler. And the market price of Chips Ahoy is $4 and Keebler's price is $3. Then, this consumer's utility for $1 becomes 10 divided by 4, which is 2.5 for Chips Ahoy, and 8 divided by 3, which is 2.67 for Keebler. Thus, this consumer may choose Keebler instead of Chips Ahoy, conditional on the prices. Assuming consumers choose the brand with the best bang for the buck, we can formulate the consumer's choice rule as follows. Keebler is chosen if the bang for the buck from Keebler is greater than the bang for the buck from Chips Ahoy. Here, the bang for the buck is given by utility from the brand divided by its price. In the numerator of the bang for the buck, which is for the utility, there are two components. Utility is consumer's attitude toward the brand in his or her mind, so we cannot directly observe utility. Instead, we can infer the utility from the data. But only some parts of utility can be identified from the data. An example is the difference between brands. In the data, market shares and product features are available by brand so the difference can be identified. Such part observed in the data is usually referred to as utility component observed by researchers. In the back-for-the-buck formula, V tilt denotes the observed utility component. However, some parts of utility cannot be observed or identified. A random, temporary fad for bread is usually not observable. Also, a consumer's mood and impulse toward the bread is not observed in data. In the back-for-the-buck formula, epsilon tilt denotes such an observed utility component. And the denominator of the back-for-the-buck, denoted P, is the price observed in the market. For expositional purpose, the choice rule can be transformed as follows. First, let's take law. Then, the multiplication and division become addition and subtraction as follows. Then, for simplicity, remove law and normalize the unobserved component. Let's assume that the standard deviation of the unobserved component is constant over the breadth, and denote beta, the inverse of the standard deviation, that is the precision, that multiplying each side of the inequality by beta, we have a normalized inequality, and replacing V and epsilon for the corresponding V tilde and epsilon tilde terms, we have this simplified choice rule equation. Now, I'm going to generalize the choice rule and derive choice probability from the choice rule. Suppose that there are capital J options in total in a product category in the market. And also, suppose that consumers can opt out of the choice. That is, they can buy nothing of the category. Let's use 0 to indicate this special option, and this option is usually referred to as the outside option. Then, the choice rule for option I is formally given as follows. Option I is chosen if and only if the observed utility minus beta times log price plus the unobserved utility for option I is greater than that for the others. If there are only two options, Chips Ahoy and Keebler, then this choice rule becomes the same as before. But from the researcher's view, the unobserved component is unknown. Thus, from the researcher's perspective, consumer choice is probabilistic. Then, the probability that option I is chosen is given by the probability that the choice rule holds over all possible values of the unobserved components. Now let's dig more down into the unobserved component. The unobserved component can be decomposed into two parts. One is demand shock, denoted eta, which implies unobserved product characteristics and quality. This shock is a market-specific shock, including a short-term demand increase by a Fed or mean. The other is idiosyncratic error, denoted E, which implies purely random component that happens to each choice occasion. It includes consumers' mood, driving impulsive buying of a brand. With the decomposition, the choice probability is now given by the idiosyncratic error is purely random, so I'm going to integrate it out in the equation. Let's assume that for all choice options, the idiosyncratic error is independently and identically distributed, for short IID, and the distribution is a standard extreme value type 1 distribution, for short EV01 distribution. Also, assume that those idiosyncratic errors are independent of all market shocks eta. Then, we have this form of the choice probability for brand I. This is usually referred to as multinomial logic. This form has been widely used in various studies because it has very convenient mathematical properties. I'm not going to explain all of those properties, but to name a few, first, it is a closed form. This means the probability value can be simply computed if we know the values of the variables in the formula. Second, the formula is simple and intuitive. The denominator is a simple sum of the numerator across all possible options. In addition to the brand subscript, now we have time subscript T in the equation. Then we can derive market shares from the choice probabilities. The most simplest way is to assume that all people in the market have identical preference. With the homogeneity assumption, the market share is the same as the choice probability. For example, all people choose brand A with probability 40% and brand B with probability 60%. Then market share becomes 40% for brand A and 60% for brand B. For further expositional simplicity, let's define delta JT as VJT minus beta times log price JT plus eta JT. This formula still has an observed component, eta. Eta denotes the market level demand shock. We need an additional treatment to handle it as an error. To do so, I'm going to introduce a share inversion method suggested by Stephen Barry, 1994. The method is very simple. As mentioned before, let's define delta JT as VJT minus beta times log price JT plus eta JT. Then, if some regularity conditions hold, there is always an inverse function of market shares with respect to delta. That is, there is always a function only of market shares to derive delta. The homogeneous multinomial logic specification satisfies all of the regularity conditions. Then, let's compute the ratio of market shares of two options, option I and the outside option. From the choice probability, the ratio of the shares is given by the choice probability for option I divided by that for the outside option. The denominator is the same for both options, so the denominators are cancelled out. Then, the ratio of the shares is given by the ratio of EXP of delta. Taking EXP, we have this simple equation. The deviation of delta J from delta of the outside option is equal to the deviation of the log market share of J from the log market share of the outside option. Without loss of generality, delta of the outside option is usually defined as 0 for simplicity. Then the deviation of delta becomes delta itself, and it is given by a function of market shares, the difference in the market share. Plugging the definition of delta into the function, We now have a linear equation that can be applied to the market level data. For expositional purpose, let me write down the equation for all options from option 1 to option capital J. This is a panel structure. At each type, we have a system of equations of the possible options. The left-hand side of equations is the log difference of observed market outcomes, that is market shares. The first part of the right-hand side of equations is the observed utility component and price term. And the remaining part of the right-hand side is the unobserved demand shock, which will be regarded as an error. In this market share model, there are several underlying assumptions. First, consumers' preference is assumed to be homogeneous. Second, consumer choice is assumed to be a multinomial logic. Third, the demand shock at top is exogenous. This implies the demand shock is independent of the price and any other market mix variables potentially included in the observed utility component V. Also, there is an additional assumption for the market share of the outside option. The market shares usually observed in the data do not consider the outside option, the option of buy nothing in the category. For example, suppose that 30% of consumers bought brand A, another 30% bought brand B, and the others, 40% of the consumers, bought nothing. Then, the market shares are generally recorded as 50% for brand A and 50% for brand B without consideration of the remaining 40%. But the market shares in the model above are the shares where the outside option is also included in the set. Therefore, the market shares in the data must be adjusted before estimating the model. An assumption is usually used for the adjustment. 1 minus the market share of the outside option is proportional to the total category demand. That is, the higher total demand is regarded as the more number of consumers buying one of products in the category. I'm going to talk about the user specification of the observed utility component. In general, the observed utility component looks like this equation. The equation consists of two components. One is brand dummies, denoted D. Those dummies assign a unique utility value to each brand. Each dummy is a binary indicator. For example, dkj becomes 1 if k equals j, and it becomes 0 if k differs from j. And each alpha indicates the brand-specific utility. For example, for the first brand, j is equal to 1, and only d1j becomes 1 and the other dummies become 0. Then, only alpha 1 is added to the observed utility. That is, this formula with dummies serves as a switch for brand-specific utility. The other component is product feature and marketing activity component. Let xjkt denote the k product feature or marketing activity for brand J. It can be a binary variable, such as whether there was a promotional add-on or not. Or it can be a continuous variable, such as the product volume or the ingredient content level, like sugar. Gamma K indicates the part worth value associated with the K feature or activity, and the sum of the part worth values is usually added to the observed utility component. From the multinomial logic specification of the market share, or the choice probability, we can compute the price elasticities. First, the own price elasticity of market share. This measures how much the market share of a brand changes in response to a 1% increase of its price. From the multinomial logic specification, the own price elasticity is simply given by minus beta times 1 minus the market share of the brand. Second, the cross price elasticity of market share. This measures how much the market share of a brand changes in response to a 1% increase of its competitor's price. From the multinomial logic specification, the cross price elasticity is simply given by beta times the market share of the brand. Surprisingly, the price level and competitors' market share do not affect the price elasticities. This is a very restrictive form of elasticities, which is a caveat of this simple market share model. Let me wrap up the lecture with some caveats of the simple market share model. The underlying assumptions used to derive the model are unrealistic and leading to potential bias in the estimates of price elasticities. First, let's talk about homogeneous preference assumption. As you know very well, no two people behave alike, and ignorance of the heterogeneity on the preference leads to a bias. For example, suppose that there are two different people. One always prefers brand A to brand B, and the other always prefers brand B to brand A. Then market share becomes 50-50. In the simple market share model with the homogeneity assumption, may estimate both brands to be indifferent for both people. That is, the model will predict a larger share for brand A if there is a price discount for brand A. However, in reality, brand A guy always goes for brand A and brand B guy always goes for brand B, regardless of the price discount. So the share will be still 50-50 even with the price discount. To control for such bias coming from the heterogeneity, some advanced techniques have been proposed. However, those techniques require understanding of high-level statistics, which is beyond this course. Those techniques will be introduced later. Another assumption enforced in the model is the multinomial logic specification of choice. This specification provides several convenient computational properties as introduced, but it also has an unrealistic property, which is called independence of irrelevant alternatives, IIA property for short. Due to this property, the price elasticity becomes a function only of the market share, which is very restricted. To resolve it, other distributional assumptions such as normal and nested logic can be replaced for the multinomial logic. But using those alternative distributions leads to the loss of the computational convenience. The share inversion does not provide a simple linear equation to be estimated. The other assumption is the exogeneity of the demand shock. In reality, the market shock is sometimes coming from or strongly correlated to the marketing activities, including pricing. For example, there could be inherent product quality which is not observed as product characteristics, and the unobserved quality is definitely reflected into the price, so high unobserved quality is positively correlated to the price. But it is not observable, so the effect of the unobserved quality may be captured through the effect of price in the model. This makes the price coefficient underestimated. The problem coming from endogeneity of the demand shock will be discussed in detail later. Alright, that's all I have in this lecture. After watching this lecture, please check out our website again for if there are additional readings and videos required or strongly recommended, online quiz assignment, and hands-on exercise in our software. Then, see you in the next lecture. Bye!